Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 2 lecture. I hope you enjoy it.
So we will be starting with some general review of Calc 1, and by that I mean just some of the things that I expect you to know already. So I'm going to call this the Calc 1 review. All right, and first let's review derivatives. And first we can start with, well, the limit definition. So f prime of x is given by the limit as h goes to 0 of the difference quotient. F of x plus h minus f of x all over h. All right, that's the limit definition of a derivative. And now let's go through a whole bunch of derivatives that you should know. The derivative with respect to x of a constant is 0. The derivative with respect to x of x to the n is n times x to the n minus 1. The derivative with respect to x of e to the x is e to the x. The derivative with respect to x of a to the x is a to the x times ln of a. All right. The derivative with respect to x of sine. Actually, before sine, let's do ln of x. That would be 1 over x. The derivative of sine is cosine. The derivative of cosine is sine. Now, before I continue here, let's look at a quick way to remember these. All right. If I'm started with sine and I'm going to make a sort of clock here. So I have SC negative S negative C. When I go clockwise on this, these are derivatives. All right. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is sine. When I go the other way, well, we'll talk about what that is. It's essentially antiderivatives when we go uh, counterclockwise. But clockwise, it would be derivatives. All right. The derivative of tangent. The derivative of tangent is secant squared. The derivative of secant is secant x tan x. Now, before we continue, let's think about a nice way to remember these. All right. Now, what I'm going to do here is I'm going to write secant, secant, tangent. All right. Now, here's the way that we're going to read this. If I'm going to take the derivative of this first one, I end up with secant times tangent. Cool. If I'm going to take the derivative of this one, I end up with secant times secant. In other words, secant squared. All right. So that's the way that you want to look at that. So perhaps I'll write this in. No, I'll just leave it as that. All right. Now, the derivative of cotangent is negative cosecant squared. The derivative of cosecant of x is negative cosecant x cotangent x. And again, let's really quickly look at a nice easy way to remember these. And I'm going to write the following. I'm going to write negative cosecant, cosecant, cotangent. And this is going to work in the same exact way as before. So as the previous one. If I start with this one right here, and I take the derivative of cotangent, I'm left with negative cosecant times cosecant. If I start with the middle one, and I take the derivative with respect to x of cosecant, I end up with negative cosecant times cotangent. So that's the way that you want to remember those. All right. Now, let's continue with some more derivatives or some more rules of derivatives that I expect you to know. I expect you to know that if I take the derivative with respect to x of f of x plus or minus g of x, well, that would just be f prime of x plus or minus g prime of x. In other words, the derivative is distributable over addition and subtraction. If I have f of x times g of x, well, this is the product rule, and the product rule says f prime g plus g prime f. All right, that's the way that I like to recall it. A lot of other professors might teach it, might make you remember this in a different way, but I like it to be written that way, f prime g plus g prime f, mostly because of the next rule. If I have the derivative of f over g, the quotient rule, all right, when I have the quotient rule is going to be f prime g minus g prime f over g squared, all right. Notice here that the numerator is essentially the product rule, but with a minus, all right, so it becomes easier to remember it this way, all right. Now, as far as proving these rules, you should have done that at some point in calculus, in Calc 1. The last one that I'll go over here, well, yeah, we're going to say the derivative of f composed with g of x. So the derivative of a composite function. Now, this essentially is just saying the derivative of f of g of x. Well, what we do here is this is going to require the chain rule. So it's going to be f prime of g of x times g prime of x. All right, and again, that last one is the chain rule. So those are some general properties of derivatives that I expect you to know coming into this class. All right. Now let's look at some integrals that I expect you to know coming into this class. So these are going to be integrals now. If I have the integral, well, actually, first let's the area under the curve is given by the limit as n goes to infinity of the summation from I equals 1 to n of f of x sub I times delta x, where delta x is b minus a over n, and x sub I star is an element in the ith interval. All right, an element of the ith interval. So that was the limit definition for finding the area under a curve. Now, some integrals I expect you to know. The integral of a constant, that's going to be kx plus c. Don't forget to do this plus c. That plus c must be written every single time we're doing indefinite integrals. All right. The integral of x to the n. The x is going to be x to the n plus 1 over n plus 1, and that plus c. That is as long as n does not equal negative 1. All right. We'll talk about that scenario in a second. But the integral of e to the x is e to the x plus c. The integral of a to the x dx, that's going to be e to the x over ln of a plus c, and that was supposed to say a to the x, sorry. A to the x over ln of a plus c. The integral of 1 over x dx. Well, the integral of 1 over x, notice here that 1 over x is the same thing as saying x to the negative 1. So the integral of 1 over x is ln of absolute value of x. plus c. And notice that I put the absolute value there. All right, it is important to use the absolute value for that. Now the integral of sine. It is negative cosine of x plus c. The integral of cosine. It is sine of x plus c. Now we can talk about here about that little clock thing that I did before in more detail. So we already said that going clockwise, it was integrals, but now going counterclockwise, going clockwise was derivatives. Going counterclockwise is going to be integrals. So if I start with sine, the integral of sine is negative cosine. The integral of negative cosine is negative sine. The integral of negative sine is cosine. The integral of cosine is sine. All right. We also have the integral of tangent. Now the integral of tangent is negative ln of the absolute value of cosine of x plus c. The integral of secant. The integral of secant is negative ln absolute value. Excuse me, not negative. This one's positive. Ln of the absolute value of secant of x plus tangent of x plus c. The integral of cotangent of x. That's going to be ln of the absolute value of sine of x plus c. The integral of cosecant of x. That's going to be negative ln of the absolute value of cosecant of x plus cotangent of x plus c. So those are all the trig functions and some generic algebraic stuff there. Now, I also expect you to know these following properties. If I have the integral of f plus g, well, plus or minus, that's going to be the integral of f plus or minus the integral of g. So just like before, I should put dx. Just like before with the derivatives, the integrals are distributable over addition and subtraction. And this next one I also expect you to know, but we will be going over anyway. It is the integral of f prime of g of x times g of x dx. That's going to be f of g of x, sorry. F of g of x plus c. Now, you may not have seen it in this format, but this is called U-substitution. And we'll go over U-substitution in a bit. Now, a few of the things that I also expect you to know. The fundamental theorem of calculus. Fundamental theorem of calculus. And there's two parts. So let's do part one. Now, part one says that if I have the definite integral from a to b of, notice I'm writing lowercase f of x dx, that's going to be capital F of b minus capital F of a. And perhaps I'll write the step in between that. The step in between that is that, well, we end up with capital F of x evaluated from b to a, which is how we get f of b minus f of a. In there, that capital F is an antiderivative of lowercase f, all right? And we would evaluate the antiderivative in those ways. Now, I just realized I wrote this in the wrong order. A goes on the bottom. There we go. All right, so that's part one. Part two. So part one essentially tells us how to evaluate definite integrals. All right. Part two tells us that if I take the derivative with respect to x of the integral from some constant to x of f of t dt, that is just f of x. All right. So essentially what that tells us is that the derivative and the integral are inverse operations. Now, let's go ahead and start 5.5. All right. So 5.5, this section should have been covered in your Calc 1 course, but I want to cover it anyway. All right. So here we go, 5.5. 5.5 is integration by substitution. So essentially this is U-sub, all right? Integration by substitution, we call it U-sub. And here we go. We're going to start with a theorem. And the theorem says antidifferentiation of a composite function so that's what the name of the theorem. All right, antidifferentiation of a composite function. And again, this is usually called U-substitution. So let G be a function whose range is an interval I, and let F be a function that is continuous. There we go. That is continuous. I abbreviate continuous as CONT. Continuous on I. If G is differentiable, and that's how I abbreviate differentiable, right? So if G is differentiable on its domain, then, and capital F is an antiderivative of lowercase f on that interval, then we get that integral that I wrote at the very end. The integral of lowercase f of g of x times g prime of x dx is given by capital F of g of x plus c. All right. If I letting u be equal to g of x gives the differential du be g prime of x dx, and we end up with the integral of f of u du, right? U was g of x, g prime of x dx is du. So f of u du is equal to capital F of u plus c. All right. So that's what we end up with there. That is the theorem. And again, that's essentially just saying how U-substitution in general works and when it works. So let's do a bunch of examples now. All right. And here we go. So let's take the integral of x squared plus 3 times 2x dx. Now, the idea here with U-substitution is that we want to make sure that whatever we make our u, then its derivative exists somewhere else on the function, all right? And ideally in a way that it would cancel it out. So let's see what happens here. I'm going to start by making u be x squared plus 3. Then du would be 2x dx, which would tell me then that dx is really just du over 2x, all right? Now that I have that, I can go back and rewrite this integral as the integral of this x squared plus 3. I didn't use it at all, so it's u. And then this 2x. Well, this 2x, I didn't use it at all. Hold on, this x squared plus 3, that was for u. Sorry, let me rephrase what I was saying here, or restate it correctly. X squared plus 3 was our u, which is why I just wrote u. This 2x, we didn't use that to figure out the substitution, so I wrote it anyway. This dx was du over 2x. What you'll note there is that the 2x's cancel each other out, and all I've got left there is just the integral of u du. And the integral of u du would be u squared over 2 plus c. But at this point, we're going to say, well, the problem here, we can't leave it in terms of u because the problem was not about u. The problem was about ux, right? It had nothing to do with u. So what we're going to say here is that we're going to end up with x squared plus 3 over 2 squared plus c. All right, and now that you have things in terms of x, we have solved it. All right, that's our final answer. So let's do a bunch of more like these. Well, a bunch of more u substitution problems. So that was A. B. Let's say I had the integral of e to the 7x dx. All right. Well, I know what the integral of e to the x is. The integral of e to the x is just e to the x. But I've got that 7 there. So let's do a u substitution to figure out what happens here. If I let u be equal to 7x, then du would be just 7 dx, which tells me that dx is just du over 7. And now let's go back to this integral over here. We end up with the integral of e to the, well, not 7x, just u, e to the u, times dx. Dx was du over 7. And now what this really says is just 1/7 times the integral of e to the u du. The integral of e to the u is just e to the u. And then we have that plus c. But again, the problem was not about u, it was about x. So what we have now is 1/7 e to the 7x plus c. All right. Next one, c. Let's say that I had the integral of x squared times the square root of x cubed plus 1 dx. All right. Now again, what we really want to use here is we want to make a u substitution. We want to make a u substitution in such a way that things cancel out. All right. And the way that we're going to do that here is, again, what we're looking for is some part of this has a derivative that's somewhere else. So in this case, I'm going to say we're going to start with u being x cubed plus 1. Then du would be 3x squared dx. So therefore dx would be du over 3x squared. All right. Now, after that, I'm going to rewrite this integral. So we have now the integral of, well, that x squared I did not use for my substitution. The square root, I'm going to change it to just be to the power of 1/2. And this x cubed plus 1, that was my substitution. And then I have dx. Well, dx was du over 3x squared. At that point, what you'll notice is that the x squares cancel each other out. And we end up with just the integral of u to the 1/2 du with a 1/3 in the front, right? This 3 goes to the front. So this now becomes, well, add 1 to the exponent. So I have 1/3 times u to the 3/2, right? 1/2 plus 1 is 3/2. And now divided by the new exponent. By dividing by a fraction is the same as multiplying by its reciprocal. So what I end up with here now is, as my final answer, is 2/9 times something to the 3/2. Remember, the problem is not about u. It's about the x over here. So what we need to do is write x cubed plus 1. All right? So that's c. And notice that I'm writing that plus c at the end of these integrals because these are all indefinite integrals. D. Let's say I had the integral of 2 secant square of x times tangent of x plus 3 dx. All right. And again, what we want to do here is, well, we want to say, well, what part of this looks like the derivative of, or that looks like it would have a derivative somewhere else here. All right. And what we're going to say here is, well, let's look at that tan of x plus 3. So I'm going to start with u being tan of x plus 3, which gives me that du would be secant square of x dx. The 3 goes completely away, right? We're taking the derivative. So, well, technically the differential. So then dx would be du over secant square of x. So this integral now becomes the integral of 2 times the secant square. We did not use it for our substitution. This tan x plus 3, that was our u. This dx was du over secant square of x. And at that point, you see that the secant square and the secant square cancel each other out. So what we really have here is just 2 times the integral of u du. And the integral of u is u squared over 2. So we have 2 times u squared over 2 plus c. These twos cancel each other out, and the problem was not about u, right? The problem was about tangent. So what we really have here is tangent of x plus 3 squared, and then that plus c. And that's his tangent. All right. So that was the E. Let's say that I had the integral of 1 over theta times, 1 over theta squared times cosine of 1 over theta d theta, right? So again, I'm going to make a substitution here. And what I really want to look at is which part of this has a derivative somewhere else. So I'm going to start with letting u be equal to 1 over theta. Because then, well, that's really just theta to the negative 1, right? And then to figure out du, that's going to be negative theta to the negative 2 d theta. So in other words, du is negative d theta over theta squared. So because of that, if I solve for d theta, that tells me now that d theta is equal to negative theta squared du. All right. So now, this integral over here, we're going to say this becomes the integral of 1 over theta squared. That was not what I used for my substitution. So I'm still going to write it there. 1 over theta squared times cosine of 1 over theta, that was my u. And then d theta, for d theta, I have times negative theta squared du. Now what we'll note there is that this theta squares cancel each other out. So we're left with the negative of the integral of cosine of u du. So we have the negative integral of cosine. Well, the integral of cosine is sine. So I have the negative sine of u plus c. But the problem was not about u. So what we have here is negative sine of 1 over theta plus c. Next one. So that was E. F. F says the integral of 3e to the 3x plus 4 times e to the 3x plus 4x to the 7/3 dx. All right. So, I mean, this looks more complicated, but it is not. It is the same exact thing that we've been doing already. All right. So in here, I'm going to start again with figuring out a u. So our u is going to be something that somewhere else we see the derivative in there. So I'm going to make u e to the 3x plus 4x because that would make du be 3e to the 3x plus 4 dx. All right, and the reason this 3 is here is because of the chain rule, right? The derivative of the outside function is e to the u times the derivative of the inside function being 3x. So that's how I get that. So from there, I can say there that dx is really just du over 3 e to the 3x plus 4. All right, so now, what are we going to do with that? Well, what we're going to say now is this integral now becomes the integral of, well, this 3e to the 3x plus 4, that was not my u, so it's still there. 3e to the 3x plus 4. This e to the 3x plus 4x, that was our u. So we have u to the 7/3, and this dx became du over 3, and that's a 3e to the 3x plus 4. And what you note there is that, unsurprisingly, those cancel each other out. So what we really have here in this problem is just the integral of u to the 7/3 du. Adding 1 to the exponent, I get u to the 10/3. Dividing by the new exponent is the same as multiplying by the reciprocal. So I get 3/10 u to the 10/3 plus c. But the problem was not about u, so it's going to be 3/10 times e to the 3x plus 4x to the 7/3 plus c. And that would be the final answer. Next one, G. So G says the integral of negative 7x to the 4th over x to the 5th plus 9 to the 2/3 dx. So again, we're doing u-substitution. So I'm going to start by saying, well, let u be equal to x to the 5th plus 9. Therefore, du will be 5x to the 4th dx, which tells us really that dx is du over 5x to the 4th. At that point, we can rewrite our integral now to say the integral of, well, this negative 7x to the 4th. We did not use that for our substitution, so it's still there. Negative 7x to the 4th over this x to the 5th plus 9, that was our u. So we have u to the 2/3. This dx was really du over 5x to the 4th. And now we see that some stuff cancels out. The x to the 4ths go away. So what we really have here is negative 7/5 times the integral of u to the negative 2/3 du. Notice that I pulled out the negative 7/5 and that I also brought the exponent up. All right, as a negative exponent. So from there, add 1 to the exponent. So I have negative 7/5 times. Add 1 to negative 2/3, that's positive 1/3. Divide by the new exponent, really means multiply by 3 in this case, and plus c. But the problem was not about u. So we need to replace that u and also distribute the 7 and 3. So I have negative 21/5 times, again, the problem wasn't about u, it was about the x. So we have x to the 5th plus 9 to the 1/3, and that plus c. So that's G. H. We have the integral of the cube root of tangent of 2x times secant square of 2x dx. All right, so in here, I'm gonna rewrite this using a couple of different things. First, I'm gonna make a theta substitution. All right, I'm gonna make a theta substitution. I'm gonna start with let theta be equal to 2x. Therefore, d theta would be just 2 dx. So dx is d theta over 2. Now, the reason I want to do that is because while I'm working with trig, and I don't want to work with these extra values here, that 2 in there, that's awful, right? We we recall identities for like secant theta or secant x, but not like secant of 2x. All right. So we're gonna get away from that 2x by using this theta substitution. Now, what does that do for us? Now, the problem now looks like, well, we have the integral of, instead of that cube root, I'm going to write this to the 1/3. But we have tangent of 2x, but 2x was theta. So what we really have there is tangent of theta to the 1/3 times secant square of 2x was theta times dx. Instead of dx, we have d theta over 2. All right. At that point, now I'm going to make another substitution. All right. Now I'm going to make our u substitution there, and I'll do it in yellow. And here I'm going to say, well, let u be equal to tan theta. Therefore, du would be secant squared theta d theta. So that d theta is du over secant squared theta. All right. And now, when I do that, I end up with the following integral. I end up with the integral of, well, that tan theta, that's our u. So u to the 1/3 times secant squared theta. We did not use that for our substitution, so it's still there. There's 1/2 I'm going to bring to the front. There's d theta. D theta was du over secant squared theta. At that point, you see that something cancels out there. We have the secant squares cancel each other out. So what I have now really is just 1/2 times the integral of u to the 1/3 du. And well, adding 1 to the exponent, I end up with u to the 4/3. We have a 1/2 over here. And dividing by the new exponent is the same thing as multiplying by the reciprocal. So what I really get there is just 3/8 u to the 4/3 plus c. But the problem was not about u. Before it was about u, it was about theta, right? Because we used u to get rid of the variable theta. So u was tangent theta. So what we have here really is, this is 3/8 times tan theta to the 4/3 plus c. But again, the problem was not about theta. Before it was about theta, it was originally about x. So we have to bring this problem back to our x. So we have 3/8 times tan of 2x to the 4/3 plus c. And now that we made our problems all about our x, now we can go ahead and move on. So that was example H. Example I. I says, well, let's take the integral of e to the 4x plus e to the 2x, plus 2e to the 2x plus 1, all of this over e to the 2x dx. All right. So in here, I'm going to first apply a rule of arithmetic here. All right. And I should say algebra, I guess. And the rule is that if I have a fraction, like a plus b over c, this is just a over c plus b over c. So if I apply that here, I end up with breaking this up as the integral of, well, let's shift that down a little bit. The integral of e to the 4x over e to the 2x dx plus the integral of 2e to the 2x over e to the 2x dx plus the integral of 1 over e to the x, e to the 2x dx. So this really just can be rewritten as the integral of e to the 2x dx plus the integral of 2 dx plus the integral of e to the negative x dx. Now in here, there are two u substitutions that we should be doing here. And in the first one, I'm going to say let u be equal to 2x. Therefore, du is x, excuse me, it's 2 dx. Therefore, dx is du over 2. Now, I don't want to use another u, So I'm going to use v. If I let v be negative x, then dv is negative dx. Therefore, dx is negative dv. All right. Now, why do I want that? Because now I can rewrite this integrals. So I have really the integral of e to the 2x. 2x was my u. Dx was du over 2. Plus the integral of 2 dx. Plus the integral of e to the v. Right, that negative x was my v. And then dx is negative dv. So times negative dv. And at that point, well, the integral of e to the u is just e to the u. So I have just 1/2 e to the u. Plus the integral of 2 with respect to x is 2x. The integral of e to the v with this negative, well, this negative is going to come to the front, making this a minus instead of a plus. And we're going to have the integral of e to the v is just e to the v. And all of this plus c. But the problem was not about u. It was also not about our v, right? The problem was not about u nor v. Before it was about u, it was about x. Before it was about v, it was about x, right? So what we have here is 1/2 e to the 2x plus 2x minus e to the negative x plus c, right? So that's what we end up with as our final answer. If you wanted to rewrite this as one fraction, again, this is a good enough final answer. But if you wanted to rewrite it as just one big fraction, you would have e to the 4x plus 4x e to the 2x minus 1, all of this over 2e to the 2x plus c. But the final answer really is good enough expanded. So that was I. Let's do J. If I have the integral of cosecant to the 5th of 7x times cotangent of 7x dx, right? The first thing I'm going to do here is, well, I see a 7x inside of trig functions. We don't like that. We don't like that. Let's just have one variable in there without any constants in front of it. So what I'm going to do here is I'm going to let theta be equal to 7x. Therefore, d theta would be 7 dx. At that point, I could say that dx would be d theta over 7. And now we can rewrite this integral. The integral now becomes the integral of cosecant to the 5th of theta times cotangent of theta times d theta over 7. All right. The next thing I'm going to do here is, well, I want to somehow use U-substitution. All right. So let's see how U-substitution is super helpful on this one. Let's make U be cosecant theta. Therefore, du would be negative cosecant theta cotangent theta d theta. And by the way, the reason I'm using cosecant theta as our u is because it's the one that's raised to the 5th power. All right. That's the only reason I'm using that. Now, let's see what happens here. When we make the substitution, we end up with the integral of cosecant was our u. So we have a 1/7 all the way to the front. Cosecant was our u. So we have u to the 5th times cotangent was not part of our substitution. D theta became, well, let's look at d theta. I never actually wrote it. D theta is du over negative cosecant theta cotangent theta. All right. But keep in mind that cosecant theta was u. So really, this just becomes du over negative u cotangent theta. All right. So this d theta over here, it's really going to be now times du over negative u cotangent theta. What you'll note there is that cotangent cancels out. But not just cotangent, this u reduces that 5 to a 4. So at that point, what we end up with here is negative 1/7. This negative came from here, right? Negative 1/7 times the integral of u to the 4th du. That's all that we're left with, right? And at that point, we say, well, the integral of u to the 4th, that's really easy. That's u to the 5th over 5 plus c. So that gives us, well, the problem is not about u. Before it was about u, it was about cosecant theta. So we have really here negative cosecant to the 5th of theta over 35 plus c. But the problem was not about theta either. It was about x. So, well, what was it? Theta was 7x. All right. So what we have here is negative cosecant to the 5th of 7x over 35 plus c. All right. Now that's just a bunch of examples on U-substitution overall. But these were all indefinite integrals. All right, let's do some definite integrals. So before we do the definite integrals, let's go over the change of variables theorem. So theorem. And this is a change of variables for definite integrals. For definite integrals. And this is what it says. If the function u equals g of x has a continuous derivative on the closed interval, so on the closed interval AB, and f is continuous on the range of g of x, then the integral from a to b of f of g of x times g prime of x dx, well, that would be integral from g of a to g of b of f of u du. All right. So what this is telling us is, well, when we change a variable to u, we also need to change the bounds. All right. It's not just the variable, it's the bounds as well. The bounds need to also reflect the change of variable. All right. So let's do some examples. All right. So let's say that I have, I get some example K. Let's say that I had the integral from 0 to 2 of 3x squared times square root of x cubed plus 1 dx. All right. And here I'm going to start by doing a u substitution. So u is x cubed plus 1. Du is 3x squared dx. Therefore, dx is du over 3x squared. But now let's look at this. I said that we also need to change our bounds, right? Now in here, what we're going to be doing is changing the bounds by considering what happens at these values of 0 and 2 into here. So when x is 0, u would be, well, 0 cubed is 0 plus 1 is 1. When x is 2, well, what would u be? Well, plug in 2. 2 cubed is 8. 8 plus 1 is 9. So what we can say now is that this integral becomes the integral from originally 0, now it's 1, to originally 2, now it's 9, of this 3x squared was not part of our substitution. This square root, I'm going to put it as to the 1/2. This x cubed plus 1, that was our u. and then this dx, that was our du over 3x squared. And what you'll note there is that the 3x squares cancel each other out. So what we really have here is just the integral from 1 to 9 of u to the 1/2 du. And notice that it is all in terms of just one variable, u. All right. Even the bounds are in terms of u. All right. So what we can do now is, well, let's integrate this. When we integrate this, well, we add 1 to the exponent, so we have u to the 3/2, divide by the new exponent, which means multiply by the reciprocal, and we're going to have this evaluated from 1 to 9. Notice now that I'm going to leave things in terms of u. Everything's already in terms of u, including the bounds. So I don't have to plug the u back in this case. We could just plug in the bounds. So what I have here is 2/3 times 9 to the 3/2 minus 9, excuse me, not 9, minus 1 to the 3/2. So we have 2/3 times, well, 9 to the 3/2. Well, 9 to the 3/2, we could apply the half first. 9 to the 1/2 is 3. 3 to the third is 27. Similarly, 1 to the 3/2, that's just going to be 1. 27 minus 1 is 26. So I have 2 times 26 over 3, which is 52 thirds. All right. Now, it is possible to not have to change the bounds. All right. If you decide to not change the bounds, then what you have to make sure you do is put everything back into terms of x before you actually evaluate it. All right. But I highly recommend that you get used to changing the bounds. So that's k. L. Let's say that I had the integral from 0 to the square root of pi of x times cosine of x squared dx. All right. So in here, the very first thing I'm going to say is, well, let's make a u substitution. I'm going to make u be equal to x squared. Du would be 2x dx, which tells me that dx is equal to du over 2x. All right. So what I'm going to do now is, well, let's see what happens with these bounds, because I got to change the bounds. All right. So when x is equal to 0, what's u equal to? Well, 0 squared is 0. All right. When x is equal to the square root of pi, what's u equal to? Well, the square root of pi squared is just pi. So what we get now is the integral from 0 to pi of this x. Well, that wasn't part of our substitution, so it's still there, times cosine of this x squared, that was our u, dx. Dx was du over 2x. So we see there that the x's cancel each other out. And what we end up with here is just the integral from 0 to pi of cosine of u du. All right. And now, well, the integral of cosine is sine. So what I have here is sine of u evaluated from 0 to pi, which means it's sine of pi minus sine of 0, which is just 0. All right. And I should make a note here that I missed out on this too. There's still 1/2 over here over 2 over 2 over 2, technically over 2, but that's just 0. All right. So again, the idea is that you have to make sure to change the bounds as well. All right. Let's do another one. So that was L. M. So let's say that I have integral from pi over 2 to 5 pi over 6 of cosine of x times sine of pi times sine of x dx. All right. So here we go. Let's make our substitution. So I'm going to make the inside of that outer sign, I'm going to make that our u. So if I make u be equal to pi sine x, then du would be equal to pi cosine x dx. Therefore, dx is du over pi cosine of x, right? And now we need to change the bounds as well. When x equals pi over 2, then u would be equal to, well, sine of pi over 2, sine of pi over 2 is 1. So u would be equal to just pi times 1, which is pi. When x is equal to 5 pi over 6, then I end up with u being equal to, well, pi times sine of 5 pi over 6. Sine of 5 pi over 6 is 1/2. All right, that's from the unit circle. And then we have 1/2 times pi, I end up with pi over 2. All right, so again, what I'm doing there is I'm plugging these values into there to figure out what the new bounds should be. So what I get now is that this integral is now the integral from originally pi over 2, now it's pi. Originally 5 pi over 6, now it's pi over 2. Of this cosine of x, that was not part of my substitution, so it is still there. Times this sine, that sine wasn't part of the substitution. This pi of sine x, that was the substitution. This dx, we said was du over pi times cosine of x, right? And that is an x. All right, so at this point, we're gonna say, well, this now is kind of weird. Because normally we have the small number in the bottom and the bigger number on top. Pi over 2 should be on the bottom, right? And pi should be on top. So we'll fix that in a second. But first, let's cancel out this cosine of x's. All right, cool. Exciting and stuff there. So now let's take this pi to the outside. So I have 1 over pi. But now let's recall a property here. The integral from a to b is equal to the negative integral from b to a. So if we reverse the bounds there, all it is just taking the negative of the integral. So I'm going to take the negative of the integral, and I'm going to write it with the small number on bottom and the big one on top. And we've got the integral of sine of u du from pi over 2 to pi. Then at that point, it's just a matter of integrating, right? Since we have the integral of sine, that's going to give us negative cosine. But with this negative that's out here, it becomes positive. So I have 1 over pi times positive cosine of u evaluated from pi over 2 to pi. And at that point, well, that just becomes 1 over pi times cosine of pi minus cosine of pi over 2. And we're going to say, well, that gives us 1 over pi times cosine of pi. Cosine of pi is negative 1 minus cosine of pi over 2. Cosine of pi over 2 is 0. So my final answer here is negative 1 over pi. All right. Now that is the end of what I want to cover from 5.6. There was a lot of examples, all right, but I wanted to give you a good refresher on U-sub overall. Now I want to briefly talk about 5.7. All right. Well, excuse me, that what we just finished was 5.5. I'm sorry. We finished 5.5. What we're gonna do right now is gonna be 5.7. 5.6 will be left to a later part of the semester. But 5.7, I want to quickly go do 5.7. 5.7 is the natural log function and integration. All right, and this is what we have. The rule is that, and I already went over the general rule, but the rule is that the integral of 1 over x dx is ln of the absolute value of x plus c. Similarly, if I say the integral of 1 over u dx, du, will be ln of the absolute value of u plus c. So that is just in general the rule of integrating something to give us a log. All right. So now let's start with this example. So the integral of 1 over 2x dx. Now I'm going to do this problem in two different ways. All right. First, I'm going to do this by saying, let's take the 1/2 out. So I have 1/2 integral of 1 over x dx, and that's going to be 1/2 times ln of the absolute value of x plus c. All right. So there we go. Now let's do this in an alternate way. So I'll do this, I call this a asterisk, and I have the integral of 1 over 2x dx. Let's say that I don't see that I can take out that 1/2, and I say, well, let's do a u substitution. Then u is equal to 2x, therefore du is equal to 2 dx, which tells me that dx is just du over 2. So at that point, what I'm going to do is I'm going to rewrite this integral, and I'm going to say, well, what I get here is the integral of 1 over u, right? That 2x was our u, and instead of dx, I've got du over 2. So I really have 1/2 integral of 1 over u du. The integral of 1 over u is ln of u, so I have 1/2 ln of absolute value of u plus c. U was 2x, so I have 1/2 ln of the absolute value of 2x plus c. Notice that I have what seems to be two different answers. And when I first did it, I had 1/2 ln of x, and now I have 1/2 ln of 2 of x. So what we're going to do here is we're going to apply some rules of logs so that you can see that these are the same exact answer. All right. So in here, I can rewrite this as 1/2 times ln of 2 plus ln of x, and then that plus c, right? All I did there was expand this ln of 2x. And I should really be using absolute values with all of these. At that point, this becomes 1/2 ln of 2 plus 1/2 ln of the absolute value of x plus c. But if I combine these two right here, right? ln of 2 times 1/2 is just some number. What number? Who cares? It's a number. It's a real number. All right? And over here, this constant is just some other number. So what I can do is I can throw this into the constant, giving me the final answer is 1/2 ln of the absolute value of x plus some new constant. Call it c sub 1. Or you can just call it c. All right? Now, these are two different ways to do this problem. It does, if you had done this second way, it would have been fine to stop here. All right, I would give you full credit, even though it looks different than this answer up here. But that is something you want to keep in mind. You want to keep in mind that your answers may not necessarily be the same answers as written in the textbook, right? When you go to check your work, you might have gotten a slightly different answer, but it doesn't mean you were wrong, all right? It just means maybe you're wrong, all right? It depends on what you wrote, right? It depends on how you simplified it. It might be just that you simplified differently. And that's something to keep in mind about all math textbooks, all right? All right, so that was A. B. Let's say that I have the integral of 1 over 3x plus 2 dx. Now here, again, I'm going to do a u substitution, and I'm going to say let u be equal to 3x plus 2. Therefore, du is 3 dx. Therefore, dx is just du over 3. And what we're going to do now is this becomes now the integral of 1 over u, right? The 3x plus 2 was u, times dx, which was du over 3. So this is just 1/3 integral of 1 over u du The integral of 1 over u is ln of the absolute value of u plus c. And we know the problem was not about u, so our final answer is 1/3 ln of the absolute value of 3x plus 2 plus c. All right. I want to do a couple of more examples of this. This is a slightly harder example. Let's say that we have the integral of x over x squared minus 3 dx. All right. Well, starts off the same way. We're going to start with saying that u be equal to x squared minus 3. Then du would be 2x dx. Therefore, dx is just du over 2x. Right? And that's our side work for the u substitution. So I'll change the color. All right. So now, what we can do now is we can say that this integral becomes the integral of this x up here was not part of our substitution. Rewrite it. This x squared minus 3, that was our substitution. This dx became du over 2x. The x's cancel each other out, so I really have here just 1/2 integral of 1 over u du, which is ln of the absolute value of u, and u was x squared minus 3. And these are still with absolute values, plus c. All right. So now let's do another one. I'll just do a couple of more. So if I have the integral of ln of x squared over x dx, all right, and I'm going to do a u substitution here. I'm going to say, well, let u be equal to ln of x. Then du would be 1 over x dx. And again, the reason I'm doing that is because, well, the reason I'm choosing u that way is because I see its derivative somewhere else on the problem, right? The derivative of ln of x is 1 over x. I see a 1 over x right there, all right? So now, what does this do to our problem? Well, let's see. If du is equal to 1 over x dx, then dx is equal to x du. So now our integral now becomes the integral of u squared over x, right? That ln of x was our u. That x we didn't use for anything. And now dx is going to be x du. So our x's cancel each other out. So we have just the integral of u squared du. And at that point, we know what that becomes. That becomes u cubed over 3, right? Add 1 to the exponent, divide by the new exponent, plus c. But we know that the problem was not about u, it was about ln of x. And that's the third power, plus c. All right. And I'll do one last one here. So that was d e. Actually, I'll do two more. E. The integral of 2x over x minus 1 squared dx. Now, at first glance, this might not look like it is a u substitution problem, all right? But it is. So let's start with what the substitution is. So we're going to start by making u be x minus 1. Therefore, du would just be dx. Now, what does that do to our integral? Well, our integral now becomes the integral of 2x, because we didn't use that for anything, so 2x over x minus 1, that's our u, so we have u squared, times dx. Dx became just du. Now, the problem here is that that x in the numerator didn't cancel out. It's still there. So we cannot integrate this as written. We still need to manipulate this some more. Now, if you look at our use of what we use for our u over here, if I solve for x there, that tells me that x is equal to u plus 1. So plugging that in, I end up with the integral of 2 times u plus 1 over u squared du. All right, which using rules of fractions, this splits up to be just the integral of 2 over u plus 1 over u squared, not 1 over u squared, what? 2 over u squared. There we go. 2 over u plus 2 over u squared du, right? Again, all I did there was apply rules of fractions. So in this first one, the integral of 2 over u, that's easy. So let's write this as two different integrals. I'm going to write it as 2 integral of 1 over u du plus 2 integral of u to the negative 2 du. All right, so at this point, the integral of 1 over u is ln of u, so I have 2 times the absolute value of ln of u, plus 2 times the integral of u to the negative 1. Well, add 1 to the exponent and divide by the new exponent. So I'm dividing by negative 1, same thing as multiplying by negative 1. And then that plus c. And then we know the problem was not about u, it was about x minus 1, all right? The problem's never about you, it's always about your x, all right? Never about you, always about the x. So we have 2 times ln of the absolute value of x minus 1 plus 2, not plus, minus, right? Because positive times a negative is negative, so minus 2 over is u to negative 1, I'm bringing it to the bottom. So x minus 1, and all of that plus c. And the last one I'll do here is the integral of 1 over x ln of x dx. And I don't know why I'm still writing in yellow. Let's put it in white. Nice. So now, in here, we're going to start with the same kind of substitution. I'm going to say let u be equal to ln of x. Then du will be equal to 1 over x dx. All right? Which tells me really that dx is just x du. Right? So now, this integral, what does it become? It becomes the integral of 1 over this x was not part of our substitution. This ln of x is our u. This dx is x du. And what we see there is that the x's cancel each other out. So I just have really the integral of 1 over u du, which is ln of the absolute value of u plus c. But again, the problem was not about u. All right? The problem is never about u. It was about x over here. So what we can say now is that this becomes ln of the absolute value of ln of x plus c. And that would be the final answer. All right, that is the end of 5.7. All right, now, so I'll stop it there.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.